Syn additions?
Yes, sir.
All right. So these are the two outcomes that you have already come across, that if any entity adds from one type of surface, it results a different isomer. If it adds from to other surface, it results a totally different isomer in fact. So this is what you have seen. If hydrogen add from this side, it results in this isomer. If hydrogen add from the other side, then it shall result this isomer. Two different isomers are forming. And if you remember, I have shown what is erythro, what is trio. Erythro is a sugar which have both hydroxyl group on same side. And if these two are opposite, this is trio. So here like substituents, if on same side, this is erythro. And if it is opposite side, it is trio in fact. So two isomers are forming which are mirror image of each. Basically they are enantiomers. So we shall always get enantiomer in exactly 1:1 ratio. This is called racemic entity, that we are getting two enantiomer in exactly 1:1 ratio in fact. Right, so this is one type you have seen. Second addition, let's see, osmium tetroxide you have come across. This bond adds here, this pi electron transfers there, and this pi electron between oxygen and osmium moves to osmium, making a electron pair on osmium here. So osmium from 8 oxidation state is changed to 6 oxidation state. Osmium tetroxide is reduced, and this olefin, because two oxygens are added to this, it is been oxidized. Fine. So what happens next? This is the process of oxidation. You shall see on next slide how this osmate converts into this entity. First, I am presenting if osmium adds from this side, it results in the formation of an isomer. If we are using cis olefin, we shall have OH here, OH here. If we are having this osmium is approaching from other side, we shall have OH, OH this side. But this is when we are starting with cis olefin. But here we are having a trans olefin. You see these RH, RH are different from each other. So this OH, these R should be eclipsed. When we are eclipsing these two R, these OH shall go opposite. So this is one isomer, this is the other isomer. If osmium is adding from this side, it shall result this isomer. If it is adding from this side, it shall result this isomer. So two different isomers are resulted by the osmium tetroxide addition to this trans olefin. So you see trans, in both cases, syn addition is taking place. If it is cis olefin, we always end with erythro. If it is trans olefin, we always will end with trio. If we have a cis olefin as well, osmium tetroxide is adding, so we shall get erythro, not trio in fact. So this is stereochemically very important aspect that you should remember. Now I'm just going in next presentation how osmate converts into this entity, how this osmium oxygen takes up. Hello. Hello.
Yes, sir.
मेरी आवाज आ रही है?
Yes, sir.
के दरमियान में इंटरप्शन हो रही थी. Right, so just look at here, what we are doing is we are using an oxidizing agent. What is the oxidizing agent? The structure number 2 I have presented, this is the oxidizing agent, and structure number 1 which I have presented, this is coming from the same slide, the written. This is the same bond presented in the rare card happen osmium. This is called NMO, N methyl
सर आपकी आवाज नहीं आ रही.
If we don't methyl heterocyclic ring, morpholing agent, this oxide it adds to osmium carbonyl type addition. So when it adds here, so we get this entity compound number 3 which is presented in this case. Now nitrogen is positively charged, it shall take this electron pair off. to stabilize positive
Sir,
charge on nitrogen. So this
sir,
oxygen shall become electron deficient. If you remember, osmium already contain a non-bonding electron pair. It shall donate that electron pair back here, and so it shall become positively charged. This hydrogen shall leave from here at the same time. So what shall happen? This neutral entity shall leave, and we shall get this osmium converting from 6 oxidation state to 8 back. Count here, osmium is bonded with 8 oxygen atoms. So what happens next? Hydrogen oxide mean water molecule adds to this. When water adds, it adds OH and loses one H positive ion, which is taken by one of this carbonyl. Very simple. One of this carbonyl moves and OH adds to this. Water molecule adds to osmium. So we are getting 2H. What happens in one case? This oxygen osmium bond cleaves and one hydrogen takes this electron pair off. What happens? You see again this osmium is in 8 oxidation state. Another water molecule adds. This is another water molecule added in this system. What happens in this case? This electron pair, you see there is another molecule. Avoid this water. This is not been added. This is just a mistake. There is no water here. So this OH was remaining, which is present written in this form. This bond with osmium oxygen cleaves and oxygen donates this electron pair off. What happens? Osmium leaves in the form of 4 oxygen double bonded with this in osmium tetroxide. It is needed catalytic amount. You see in previous slide, it started with osmium tetroxide, and in the end it is being converting into again osmium tetroxide. It has a catalytic role. In fact, osmium tetroxide is here used as a catalyst. So what it is resulting, both OH are eclipsing each other in fact. So this is how the outcome are presented. So if it is this one, this is how it is being hydrolyzed. So this is the method how oxidation takes place. This is the mechanism I have highlighted in this presentation. So you have come across olefinic electrophilic addition. So in that case, you have come to know 2 type of addition, syn addition and anti-addition. So syn addition you have come across always takes place in concerted, following a concerted mechanism, single step. So this is a single step, this is a single step, but you argue that it is taking more than one step. In fact, the next step, this is not an addition step. This is how to remove this osmium from this oxygen, right? So this is an oxidation step. It is not a single step. Even you see there are so many number of steps involved in this cleavage. So this is the cleavage of this one, but in fact it is simply the addition is taking place in the very first step. This is single step. Concerted mechanism it is involved in. So it is resulting in the formation of a trio in this case. The next one, if I am interested to present, is anti-addition. What is anti-addition? Anti-addition you have already come across that one of the entity, not necessarily the B. So one X leaves with electron pair. So this X shall become electron deficient. What shall happen? This electronic density from pi electronic density shall be transferred to this X in fact. If it is transferring to this one, this pi electronic density is electron deficient in fact. So one of the carbon shall become electron deficient. At the same time, this X, which is making a bond with this, also have a non-bonding electron pair. It shall donate this electron pair back to this one. So what we are getting, this X first bonded with this, and then it donated the electron pair to the rear carbon. Let's say if front carbon is making a bond with this, then this X donates back an electron pair to rear carbon to make a bond which is presented in red in fact. So because it is halogen, chlorine, X is chlorine, bromine or iodine. So these are halogen, it is monovalent. It only make one bond. But when it is making 2 bond, mean it has shared one non-bonding electron pair with rear carbon. So it is positively charged. Now look at here, one X negative was removed. This one, it is adding to this one. Once it adds to this, this is the structure number 3. If you look at this X is already present. Now it was bonded double. So this rear carbon is the bond with the X is bonding with the approaching the rare carbon. So bond with rare carbon shall break. Now you can see this is the same presentation I have made in the other just before these two slides back in other mechanistic studies. So this R shall transfer here, this H shall transfer here to make a 120-degree angle. So which shall acquire this position. Now this can be presented in this way. What if I make this R and eclipsing with R, then what shall happen? If this R is eclipsed with this hydrogen shall eclipse with this X shall eclipse with this, resulting in these hydrogen and X are eclipsing. So this hydrogen and X are eclipsing, hydrogen and X are eclipsing. So this is a trio combination. You see, both like atoms are opposite to each other. So this is the trio product. Initially, you have seen trans-olefin, but in syn addition. Here it is cis-olefin, but anti-addition, resulting both trio. So this is the outcome coming out of this. This is one I have presented, but let's see. This X doesn't approach front rare carbon; it approaches front carbon. Here it is presented. This is approaching the rare carbon, but let's say if this approach front carbon, then this bond with front carbon shall break, and this R shall transfer to this position. This H shall transfer to this position. It is presented likewise. Now you can see, now if I make them eclipsing with each other, now both of these X shall be present at these two hydrogen and they shall be opposite. You see, this substrate is different, this substrate is different. So if it is approaching from this side, both isomers are forming in exactly 1:1 ratio. This is something what we call anti-addition. So let's say if I quote another example in this case, this molecule that I have presented here, this one, this is called meta-chloroperbenzoic acid. In benzoic acid, you are having carboxylic O bonded with H, carboxylic acid. This is not a carboxylic acid. You see, this is a hydrogen peroxide bonded with carbonyl, which we call per acid. So meta-chloroperbenzoic acid. This is not simple benzoic acid. This is perbenzoic acid. And at meta position, we have a chloro. So it is meta-chloroperbenzoic acid. MCPVA, what stands for? So meta-chloroperbenzoic acid, it stands for. So this is a molecule. If you look at this oxygen, its lone pair is involved in resonance. So this is delocalized. But look at this oxygen, the non-bonding electron pair present on this oxygen is not involved in resonance. So this oxygen participates. It, in fact, just what we are observing here, this is our atom A, this is atom B. This is adding and this is leaving. Just you have seen in previous example, like atoms, one is taking electron pair off, other is electron deficient. This is the same. Oxygen, oxygen bond. One oxygen is taking this electron pair off, right? It is contributing here. So this shall contribute it here. And this hydrogen is losing this electron pair. Oxygen is donating this electron pair here, and this pi electronic density is transferring to this oxygen, resulting in the formation of this oxygen making two bonds. Now, if it is making two bonds, it has oxygen. There is no full charge because oxygen can make two bonds in fact. And what is leaving? Benzoic acid. This is called MCBA, metachlorobenzoic acid. This is MCBA. This is MCPBA. You see, reduced. Oxygen has been removed from this. This is been reduced. MCPBA is reduced and olefin is oxidized. Now just compare, in previous example, we were using cis-olefin anti-addition. In this one, we are using trans-olefin and anti-addition, right? So what this results? This results in this entity that we three-membered ring is formed. This is called epoxide. This is the functional group. Three-membered ring, commonly called oxirane. This is the IUPAC name given, but commonly this is called epoxide. What you have the binders, adhesives that you normally use, epoxies. So epoxy, which is used for joining some things to each other. So that basically contain this functional group, epoxy, three-membered ring with oxygen rings, epoxy groups. So this is commonly called epoxides. In fact, epoxides are highly reactive. One reason they are three-membered ring, two carbon, one front carbon, one rear carbon bonded with oxygen. This is a three-membered ring. In fact, now there are two possibilities. This water molecule can approach to rare carbon, so rare carbon bond with oxygen shall break, or it shall result in the formation of this bond with rare carbon. With front carbon there is already present, or another possibility, this water can approach front carbon and rare carbon bond, front carbon bond shall break. So in that case we shall get this possibility. This one is equal to this one, and this one is equal to this one. Now you can see this product which is here and this product which is here, both like atoms are on same side. So here these are resulting erythro. Look at here in this example and previous example. In both example, anti-addition is taking place. It is taking place one step, generating an intermediate, then it is going to form the final product. Two steps are involved. This is stepwise. So this is anti-addition. But in this case, anti-addition. But what is happening? That this is happening on a trans-olefin. Trans-olefin anti-addition results always erythro, and cis-olefin anti-addition always result trio products. So this is the key of the results that we are interested in to present, that syn addition and anti-addition are totally different from each other. Syn addition involves a concerted mechanism, anti-addition involves a stepwise mechanism. And not only this, it also depends upon the configuration of the olefin. If olefin is cis, syn addition shall give you erythro entity. If we have a trans olefin, syn addition takes place, so it shall result in the formation of a very simple trio products, but not only one, two trio, two erythro shall always form. And similarly, if anti-addition is taking place, in previous example, this one, you have come across cis-olefin. When anti-addition takes place, it results in the formation of trio entities. But on the other hand, if we are using trans-olefin, anti-addition is taking place, this is resulting erythro entities. So in all cases, we get two erythro products. So here this erythro, this is also erythro product. And in previous, we are having cis-olefin, so we are having these are the two trios. So this is very simple to see. If we start with cis-olefin, syn addition shall give you erythro entity. If you have a cis-olefin, anti-addition shall give you trio, not erythro. This is the difference. We have fixed one entity. We have fixed the olefin. Syn addition shall give you erythro entities. Cis-olefin anti-addition shall give you trio entities. This is very important to understand. On the other hand, if you look at anti-addition, if with respect to syn addition, if we have cis-olefin, syn addition taking place, resulting erythro, cis-olefin anti-addition giving you trio. If it is opposite, if you are starting with a trans-olefin, syn addition shall give you trio, and trans-olefin anti-addition shall give you always erythro entities. So this is a stereo control that we can adopt in fact. So this is all about the electrophilic addition that we come across in the very beginning of this course. So I have covered this part of the system, that if we have a carbon-carbon double bond, so electrophile can be reacted with this olefin. So olefin donates electronic density to this. So in next lecture, you shall see how this electrophile approach olefin. So I shall make a molecular orbital approach to explain this. So next lecture shall be also on addition reaction, electrophilic addition. Then we shall focus on nucleophilic addition across this. Then we shall go to these type of systems later. All right. So any question?
Excuse me, sir.
Any question if there are?
Yes,
Sir,
sir.
जो oxidation of osmosis.
हाँ जी,
Yes, sir.
पूछे भाई।
सर जो आपने ऑक्सीडेशन ऑफ ऑस्मेट बताया था उसके अंदर ऑक्सीडाइजिंग एजेंट का नाम क्या था? आवाज कट गई थी
NMO.
आपकी उस वक्त।
NMO.
सर,
This one.
सर उसका फुल नेम क्या है? सर उसका फुल नेम क्या है?
N-methyl morpholine oxide.
ओके
N-methyl morpholine oxide. This structure number 2. This is N-methyl morpholine oxide.
सर ये
ओके
वाली दो
और
steps
सर
बता दें।
हाँ जी।
सर ये वाली जो कन्वर्जन हो रही है यानी ऑक्सीजन कनेक्ट हो रही है और उसके बाद जब ये एन मॉर्फोलिन रिमूव हो रहा है, सर ये स्टेप्स थोड़े से आप बता दें। तो आपकी उस वक्त आवाज बहुत कट रही थी।
But this is simple carbonyl type addition. Why we call this osmate? If you remember the esters, what are esters? If you remember, you are having a carbonyl carbon bond. On one side, this carbonyl is bonded with hydrogen or alkyl group. On other side, it is bonded with oxygen, and oxygen is further bonded with alkyl group. This is commonly called ester. So esters are normally
Yes, sir.
like acetate, propanoate, they end with ate. So this is also ending with 8. Why we are ending this with 8? This is just like carbon oxygen double bond. And look at other side, this is bonded with oxygen. Oxygen is bonded with carbon. So this is an ester. But this is not a simple ester. Because here we have two carbonyl and two oxygen bonded with alkyl group. That's why this is called osmate, mean an ester.
ओके
So ester addition, very simply, any nucleophile when approach carbonyl carbon, this is very similar here. This is a nucleophile, oxygen carrying a negative charge. It shall approach, this is electron rich, osmium is electron deficient. So in this case, this
यस
electron
सर
pair shall transfer to oxygen, and this oxygen shall make a bond with this. Because osmium is having 6 oxidation states, when this is adding, the oxidation state shall remain same, unchanged. You see here, osmium is bonding with 6 oxygen. Here it is also bonded with 6 oxygen.
यस सर
Right? Anything else?
सर बट हाउ दिस ऑक्सीडेशन स्टेट चेंजेस टू 8 स्टेट?
In this case, this nitrogen is positively charged. So this positively charged nitrogen is leaving with the electron pair to stabilize positive charge on nitrogen. So this oxygen shall be positively charged. This positive charge is stabilized by this osmium. It donates this electron pair back. Where this electron pair is coming on osmium, just remember here. When this addition was taken place, this pi electronic density was transferred on osmium. So this an
यस
electron
सर
pair is moved to osmium, mean an non-bonding electron pair is present on osmium. When addition was taken place, osmium from 8 was changed to 6. So osmium
यस
had
सर
a one non-bonding electron pair. This is that non-bonding electron pair I have presented. So it donates this non-bonding electron pair here to stabilize positive charge on the oxygen. Now, if it takes, it shall be in 7. 7 is not a stable oxidation state. So that's why what happens, this hydrogen leaves and converts osmium into 8 oxidation state. Now you can count oxygen is bonded with 2, 4, 6, 7, and 8. 8 oxygens.
8
That's why it
बॉन्ड्स
has
यस
8
सर।
oxidation state.
तो सर ऑस्मियम 8 स्टेट के अलावा यहाँ से रिलीज नहीं हो सकती है? 6 स्टेट में नहीं रिलीज हो सकती?
G9. It is not a stable
ओके
oxidation state.
ओके थैंक यू सो मच सर।
Any other question? Right, so the last slide that I have presented yesterday, this is about the suggested reading. So after 1 or 2 days later, I shall share with you these slides, and I shall provide here a few exercise questions. which are associated with this. So just keep reading these pages from 427 to 445. All of you have the e-copy of this?
Yes, sir.
Anyone who don't have the
Yes, sir.
e-copy of this book? If every one of you have, just go through to page number 427 to 445.